Hello everyone, this video is about inference for a single population mean. Specifically, we are going to look at how to conduct hypothesis testing for population mean, and we'll see how to construct a confidence interval. So in making inference for a single population mean, we are going to consider a single group or population for which the conclusions are going to be made. And from this single group or population, we are interested on a single quantitative outcome variable, let's say x of interest, and this quantitative outcome variable is assumed to have a normal distribution with population mean mu and population variance sigma square. So for this outcome variable of interest, we write the distribution as x as a normal distribution with mean mu and variance sigma square. So here the objective is to make inference for the population mean mu, because these parameters mu and sigma square are unknown. So specifically, we are interested in testing a particular value for that of the population mean, assuming that of sigma square is either known or estimated from certain sample data. So here is the question of interest is to determine whether a particular value, let's say mu naught, is plausible for this population mean or not. So to make inference or conduct hypothesis testing, we need a certain random sample of observations, let's say x1, x2, xn observations taken from that particular population or group. So using these sample observations, we can determine that of the sample mean as 1 over n times the sum of xi, and the sample variance can be estimated as 1 over n minus 1 times the sum of the square of the deviation of each value taken from the mean value. Then using this summary statistics calculated from the sample selected from the population of interest, first you need to state that of the null and alternative hypothesis. And as we have seen in the previous video, we could have 3 different options for conducting or for stating the hypothesis for making hypothesis testing. So the first option is to state mu equals mu naught under the null hypothesis and mu different from mu naught under that of the alternative hypothesis. So this is a two-sided test or two-tailed test. Or we may make the alternative hypothesis as mu less than mu naught. This is a one-sided test, and specifically it is called left-tailed test or left side test. And we could also make mu greater than mu naught for that of the alternative, and here again this is a one-sided test and it is particularly right-tailed test. So we have to state either of these 3 options in stating that of the null and alternative hypothesis. Then once we state our null and alternative hypothesis, next we have to specify the level of significance alpha, which is the probability of committing type 1 error, and we have to obtain the corresponding critical or tabulated value from the theoretical statistical distributions, either from standard normal distribution or that of a t-distribution. So if our hypothesis is a two-sided alternative hypothesis, or if it is a two-sided test, the tabulated value is going to be calculated as T alpha over 2. Now here capital T could be either the normal distribution or the t-distribution. And for that of a one-sided test, the tabulated value of the test statistic is going to be determined as T alpha. Then once we determine the tabulated value, next we have to determine the appropriate test statistic, and we have to obtain the calculated value using that of the sample data. And here we could have again 3 different cases. So if the population variance or population standard deviation is known, the calculated value of the test statistic is based on that of a standard normal distribution, and it can be determined as the sample mean minus mu. Actually, this mu is mu naught, which is assumed under the null hypothesis. So under the null hypothesis, we assume that the population mean mu is not significantly different from the assumed value mu naught. So here in the test statistic, in place of mu, we have to substitute it by mu naught. So the calculated value is x bar minus mu over the population standard deviation over root n. Therefore, this will have a standard normal distribution, which has a mean of 0 and variance 1. But if sigma is not known, and if we know that n is large, specifically if n is greater than or equals to 30, now the calculated value of the test statistic is also based on that of a standard normal distribution, and it is calculated as x bar minus mu over the sample standard deviation divided by root n. So as long as the population variance is known, or the sample size is large enough, or particularly greater than or equals to 30, we can use that of the standard normal distribution. But if the population variance or population standard deviation is not known, and if the sample size is small, specifically if the sample size is less than 30, in that case, the test statistic will be based on that of a t-distribution, which has n-1 degrees of freedom. And the calculated value of the test statistic will be just similar to that of this one, x bar minus mu over the sample standard deviation divided by root n. Then once we determine the calculated test statistic and that of the tabulated value, next, to make a distinction, we need to compare the absolute value of the calculated test statistic and that of the tabulated value. So in absolute value, if the calculated value is greater than or equals to that of the tabulated value, or if the p-value is less than that of the specified significance level, in that case H0 can be rejected, and we call that the test is significant. Then based on the decision whether H0 is rejected or not, finally we will have a conclusion. So now let's consider an example to illustrate how we can conduct hypothesis testing following this procedures, stating the null and alternative hypothesis, and then specifying the level of significance and obtaining the critical or tabulated value, and then obtaining the of the calculated value of the test statistic, and by comparing the calculated value of the test statistic with the tabulated value, we'll decide whether to reject or not to reject the null hypothesis, and finally, based on our decision about H0, we'll have a conclusion. So here the example says the life expectancy of HIV patients is expected to be 50 years. A survey was conducted on 11 patients of a certain hospital, and the data obtained as 52.2, 58.2, 56.6, and then lastly 57. So the question of interest is, does the data confirm the expected view? That means, does the data confirm that the life expectancy of HIV patients is as expected, that's of 50 years? So with this data, we have these sample observations consisting of 11 observations. So the sample size is 11, and from this we can easily determine the sample mean, which is 1 over n, that is 11, times the sum of the xi's, or the sum of these values. So the sample mean becomes 54.41. And similarly, the sample variance can be calculated as 1 over n minus 1, which is 1 over 11 minus 1, times the sum of the square of the deviation of each value taken from the mean. then the sample variance becomes 23.607. Similarly, the sample standard deviation is nothing but the positive square root of the sample variance. So root of 23.607 becomes 4.859. So based on this data, we have obtained these summary statistics, specifically the sample size, the sample mean, and thus of the sample standard deviation. So here the parameter of interest is the mean life expectancy of HIV patients, or population mean life expectancy of HIV patients, and that is denoted by this the Greek letter mu. And the assumed value here is 50. That is, it says the life expectancy of HIV patients is expected to be 50 years. So 50 is the assumed value for the population mean life expectancy of HIV/AIDS patients. So mu naught, or the assumed value that's going to be considered under the null hypothesis, is 50. So first we have to state the null and alternative hypothesis. So the first one is H naught, which states there is no difference between the population mean and the assumed value. So we write as H naught mu equals 50. That is, the mean life expectancy of HIV patients is not significantly different from 50 years. And the alternative, because we are interested in testing whether the mean life expectancy is around 50 or not, so the alternative hypothesis should be a different from type. So from the question that's given, the direction is not clear. Just the interest is whether the life expectancy is 50 years or not. So the direction is not specified. So the alternative hypothesis should be a different from type, which could be the population mean life expectancy greater than 50 or less than 50. So the alternative hypothesis states the mean life expectancy of HIV patients is significantly different from 50 years. So here when you say the mean life expectancy, this is the population mean life expectancy. So in specifying these assumed values for this parameter of interest, we are talking about the population mean. And this population mean, or the assumed value for the population mean, is going to be tested using that of the sample values, which provides the sample mean and the sample standard deviation. So statistically, for example, when we write as mu equals 50, it doesn't mean that the mean life expectancy of HIV patients is exactly 50 years. So instead of saying exactly 50 years, we have to say the mean life expectancy of HIV patients is not significantly different from 50 years. So in the null hypothesis, actually, this mean life expectancy may not be exactly equals to 50. It may have a small difference, but that small difference is not really significant. So the statement under the null hypothesis doesn't necessarily mean that the mean is exactly equals to 50. Rather, it is to mean that the mean life expectancy is not significantly different from 50. But in the alternative, yes, it is significantly different from 50, which could be greater than 50 or less than 50. Next, the level of significance is not specified. So here, if the level of significance or the probability of committing type 1 error is not specified, we can consider as 5% usually, or as a default value. The value of alpha is assumed to be 5% or 0.05. And here we have a sample of 11 observations, and the population variance or population standard deviation is not given or is not known. So here the distribution that we are going to utilize is that of the t distribution. So the distribution is t distribution. So based on this t distribution, we have to obtain that of the tabulated value. So T tabulated is nothing but T alpha over 2, and the T distribution has that's of n minus 1 degrees of freedom. So here we make T alpha over 2 because here the alternative hypothesis is a different from type. If it was a one-sided alternative hypothesis like less than 50 or greater than 50, here we would have to make this as T alpha. But for now it is mu is different from 50, so we have to divide the level of significance into 2. So the tabulated value of the test statistic based on the T distribution is T alpha over 2 with n minus 1 degrees of freedom. So this becomes T 0.025 with 10 degrees of freedom. So you can obtain this value directly from a T distribution, which becomes 2.228. Then once we obtain this tabulated value based on the theoretical T distribution, next we have to obtain the value of the test statistic. So the test statistic is also based on that of a T distribution. So the calculated value of the test statistic is the sample mean minus the assumed value under the null hypothesis, which is 50, divided by the sample standard deviation divided by root n. So we already obtained the sample mean as 54.41 minus 50, this is the assumed value under the null hypothesis, divided by the sample standard deviation 4.859 divided by root of the sample size, that is 11. So this becomes 3.01. So we have to compare this calculated value of the test statistic with the tabulated value of the T distribution. So here this calculated value 3.01 is greater than 2.28. That means H naught should be rejected or the test is significant. So the calculated value is 3.01, which is greater than the tabulated value, which is 2.228. So H naught can be rejected, or we can say the test is significant. We can also calculate the p-value, which is 2 times the probability that a T distribution with 10 degrees of freedom has a value greater than 3.01. Actually, we can determine this using statistical software. We cannot directly obtain it from the T distribution, but we have to use statistical software to obtain this value. So the p-value will be 0.0132. This p-value is less than that of the specified level of significance, which is 0.05. So again, using this p-value, H naught can be rejected. Then H naught can be rejected means there is sufficient evidence to reject the null hypothesis, or there is sufficient evidence against the null hypothesis, which states that the mean life expectancy of HIV patients is not significantly different from 50 years. So if the mean life expectancy is not significantly different 50 years, if it is rejected, that means in particular, since the difference is here positive, we can say that the mean life expectancy of HIV patients is significantly larger than 50 years at 5% level of significance. So it is a two-sided alternative hypothesis test, but once we reject this null hypothesis, that means we are in favor of this alternative hypothesis. So mu may be greater than 50 or mu may be less than 50. So we have to identify the direction and specifically just since the difference here it is positive, or is the difference x bar minus the assumed value, it is positive. So we can say that the mean life expectancy of HIV patients is significantly larger than 50 years. Let's consider another example. The thermostat in a classroom is set at 72 degrees Fahrenheit, but we think that the thermostat is not working well. So on 7 randomly selected days, let's assume that we measure the temperature at our seat in degree Fahrenheit and obtain the values as 71, 73, 69, 68, 69, 70, 71. Then here the question of interest is to test whether the mean temperature at our seat is significantly different from 72 degree Fahrenheit at 99% confidence level. So here the population parameter of interest to be tested for is as of the mean temperature of the classroom. And 72 degree Fahrenheit it is assumed value under the null hypothesis. And here we have the sample values. And we have given 99% confidence level. That means the significance level is 1% or 0.01. So based on the data that we have, we can calculate the sample mean as 70.14 and the sample standard deviation as 1.68. So here's the parameter of interest is the population mean temperature of the classroom. And here's the assumed population mean is mu naught, which is 72 degree Fahrenheit. So we are interested whether 72 degree Fahrenheit is a plausible value for the population mean temperature of the classroom. So we have to state first that of the null and alternative hypothesis. So H naught mu equals 72 degree Fahrenheit, which means the mean temperature of the classroom is not significantly different from 72 degree Fahrenheit. And the alternative, it states that the mean temperature of the classroom is significantly different from 72 degree Fahrenheit. So again, the alternative hypothesis is a different from type. Therefore, here we have a two-sided alternative hypothesis test, or it is a two-sided test. And we have given the 99% confidence level, so the level of significance is 1% or 0.01. And again, the sample size is small, that's less than 30, and the population variance or population standard deviation is not given. So again, the distribution that we are going to use is t-distribution. So similar to the previous one, the tabulated value of the test statistic is t alpha over 2 with n minus 1 degrees of freedom, which becomes 3.707. And again, we have to obtain the calculated value of the test statistic, which is obtained as x bar minus mu naught, the s over root n. So this tabulated value becomes minus 2.929. Now here we have the tabulated value based on the theoretical t-distribution, and here we have the calculated value based on the data. So we are going to compare the absolute value of the calculated test statistic with that of the tabulated value. So if you consider the absolute value here, it becomes 2.928. 2.928 is less than 3.7. So that means here H naught cannot be rejected. So here the calculated value of the statistic is 2.929 in absolute value, which is less than that of the tabulated value. Therefore, H naught cannot be rejected. So that means there is no sufficient evidence against the null hypothesis, or there is no sufficient evidence to reject the hypothesis that states the mean temperature of the classroom is not significantly different from 72 degree Fahrenheit. So there is not sufficient evidence to reject the null hypothesis. In other words, the mean temperature of the classroom is not significantly different from 72 degree Fahrenheit at 1% level of significance. And let's consider another example again. A researcher is interested to examine the cholesterol levels in women of age 18 up to 30, but she or he did not have any prior information about the distribution of cholesterol levels in such women. It was known that the distribution of cholesterol levels in women aged 31 up to 50 is known to be approximately normal with a mean of 190 milligram per day. So the interest is on women of aged 18 up to 30, but this mean is for that of women aged 31 up to 50. Then the researcher wanted to evaluate whether the mean cholesterol level differed from the mean cholesterol level of middle-aged women. So the interest is whether the mean cholesterol level of women of aged 18 up to 30 is different from that of women aged 31 up to 50. That means we are interested in testing whether the mean cholesterol level of women of aged 18 up to 30 is significantly different from that of 190. So a random sample of 100 females aged 18 up to 30, which is our population of interest, was selected, and the selected females were administered blood tests that yielded cholesterol levels having a mean of 178.2 milligram per dl and a standard deviation of 45.3 milligram per dl. So the question of interest is there significant evidence in the data to demonstrate that the mean cholesterol level of females of aged 18 up to 30 differs from 190, which is actually the mean cholesterol level of women aged 31 up to 50. So our parameter of interest is the mean cholesterol level in women of aged 18 up to 30. The assumed value here we have 190, and sample data is already collected from, let's say, that's of 100 females, and the mean value is here 178.2 and the standard deviation 45.3. So using those summary statistics, which are just the sample mean cholesterol level and that of the sample standard deviation, we can test for whether the mean cholesterol level of females aged 18 up to 30 is significantly different from 190 or not. So first we have to state the null and the alternative hypothesis. So the null states that mu equals 190. That means now mu stands for the mean cholesterol level of females of aged 18 up to 30. So the mean cholesterol level of these females aged 18 up to 30 is not significantly different from 190. And the alternative, again, the direction is not specified, so we have to consider that of a different from alternative hypothesis test. So it is mu different from 190. So the level of significance is not specified here, therefore we have to consider that of 5% or 0.05. And here now the sample size is 100, which is greater than 30. Therefore here we have to consider that of the standard normal distribution or Z distribution. So the tabulated value based on Z distribution becomes Z alpha over 2 now. Now for a standard normal distribution, the parameters are the population mean and thus of the population variance. We do not have a degrees of freedom. So we have to write the tabulated value as Z alpha over 2. Alpha is divided by 2 because we still have a different from alternative hypothesis. And Z alpha over 2, this becomes Z 0.025, which is 1.96. Now here we obtain the tabulated value. Next we have to obtain that of the calculated value of the test statistic based on the standard normal distribution or Z distribution. So the calculated value of the test statistic is x bar minus mu naught, which is the value assumed under the null hypothesis, that is 190, divided by the sample standard deviation divided by root n, or the sample size. So it becomes 178.2 minus 190 divided by 45.3 over root 100, and this becomes minus 2.60. Now here we have the tabulated value of the test statistic as 1.96 and the calculated value of the test statistic as minus 2.60. So we need to compare these values. So taking the absolute value of this calculated test statistic, which is 2.60, is going to be compared with that of this tabulated value 1.96. So here 2.60 is greater than 1.96, therefore the null hypothesis should be rejected. So the calculated value in absolute value is 2.60, which is greater than the tabulated value, which is 1.96. So the null hypothesis can be rejected. So this indicates that there is sufficient evidence against the null hypothesis, which states that the mean cholesterol level of females of aged 18 up to 30 is not significantly different from that of 190. So our conclusion is the mean cholesterol level of females of aged 18 up to 30 is significantly different from 190 milligram per del at 5% level of significance. And in particular, since the difference is negative, we can conclude that the mean cholesterol level of females of aged 18 up to 30 is significantly less than 190. So compared to that of females aged 31 up to 50, the mean cholesterol level of those women aged 18 up to 30 is somewhat less than 190. So this will be our conclusion, that the mean cholesterol level of the females of aged 18 up to 30 is significantly less than the mean cholesterol level of those females of aged 31 up to 50. And let's consider one more example again. So this one says, as the public concern about bacterial infections increases, a soap manufacturer quickly promoted a new product to meet the demand for an antibacterial soap. This new product has a substantially higher price than the ordinary soaps on the market. A consumer testing agency notes that the ordinary soap also kills bacteria and questions whether the new antibacterial soap is a substantial improvement over the ordinary soap. So in terms of price, the new products or the new soap has higher price, but the question of interest is whether this new antibacterial soap has a substantial improvement compared to that of the ordinary soap. So from previous studies, using many different brands of ordinary soaps, the mean bacteria count is 33 for ordinary soap products. Then the consumer group runs a test on the antibacterial soap, which is the new one, using 35 petri dishes, and it yielded a mean bacterial count of 31.2 with a standard deviation of 8.4. So here it says, do the data provide sufficient evidence that the antibacterial soap is more effective than that of the ordinary soap in reducing bacteria counts? So here it is given that from previous studies using many different brands of ordinary soaps, the mean bacterial count is 33. So for the new antibacterial soap, an experiment is conducted on 35 petri dishes, and it yielded a mean bacterial count of 31.2 and standard deviation 8.4. So the value assumed under the null hypothesis is going to be 33. And 35 is the sample size, 31.2, it is the sample mean, and you have 8.4, that's of the sample standard deviation. And here we are interested in testing whether the new antibacterial soap is better than that of the ordinary soap. So in order for this new antibacterial soap to be better than the ordinary soap, the bacterial count should be significantly less than that of the ordinary soap. So here the population parameter of interest is the population mean bacterial count for the new antibacterial soap. So we are interested in testing whether this mean bacterial count is significantly less than that of 33, which is actually the mean bacterial count of the ordinary soap. So 33 is the mean bacterial count for the ordinary soap that's going to be used as a reference for that of this new antibacterial soap. So regarding the hypothesis, H notes states that the mean bacterial count of the new antibacterial soap is not significantly different from 33. And the alternative is, here in order for the new antibacterial soap to be effective, the mean bacterial count should be less than 33. So here we have to state the alternative hypothesis as H1 mu less than 33. Therefore here we have a one-sided alternative hypothesis, or here the test is one-sided test or one-tailed test, and specifically it is a left-tailed test. So this alternative hypothesis states that the mean bacterial count for the new antibacterial soap is significantly less than 33. That means the new antibacterial soap is more effective than the ordinary soap. So if H note is rejected, the new antibacterial soap is more effective. Otherwise, if H note is not rejected, there is no sufficient evidence to claim that the new antibacterial soap is more effective than the ordinary soap. So next we have to specify that of the significance level. Here the significance level is not specified, so we have to consider that of a 5% level of significance, or alpha equals 0.05. And here the sample size is 35, which is actually greater than 30. So we have to consider that of a standard normal distribution, or Z distribution. So based on the standard normal distribution, we have to obtain the tabulated value or critical value. And this tabulated value is nothing but Z alpha. Now we make it Z alpha instead of Z alpha over 2, because here we have a one-sided alternative hypothesis. So this is Z alpha. So this becomes Z 0.05, and the value 1.645 can be easily obtained from a standard normal distribution table. And next we have to obtain the calculated value of the test statistic. This is x bar minus mu naught, which is the value assumed under the null, that is 33, divided by the sample standard deviation divided by root of the sample size. So it becomes 31.2 minus 33 over 8.4 divided by root of 35. This becomes minus 1.27. So we are going to compare the absolute value of this value with that of the tabulated value obtained from the standard normal distribution. So in absolute value, this value becomes 1.27, and this is less than 1.645. Therefore, that means here there is no sufficient evidence to reject the null hypothesis. So here is the calculated value of the test statistic, which is 1.27 in absolute value, is less than the tabulated value. Therefore, H naught cannot be rejected. That means there is no sufficient evidence to claim that the new antibacterial soap is more effective than that of the ordinary soap. Therefore, the mean bacterial count of the antibacterial soap is not significantly less than 33 at 5% significance level. So even if the price is somewhat higher, in terms of effectiveness, there is no sufficient evidence to claim that the antibacterial soap is more effective than the ordinary soap at 5% level of significance. Now let's go to that of the construction of a confidence interval for a population mean. Now, as you have seen in the previous video, the sample mean is a point estimate for the population mean, but the sample mean is a single value, therefore it's not possible to determine how close this sample mean is to that of the population mean. So it's better to construct a certain range of values, or let's say a confidence interval in which the assumed population mean is expected to lie within a certain degree of confidence. So confidence interval determines the range of plausible values for which the null hypothesis H0 is not rejected. So here we are going to consider a certain range of values for which the assumed population mean is expected to lie with a certain degree of confidence. So for those values in the interval, the null hypothesis is not going to be rejected. So using that of the methods of calculating for the test statistic, we are going to consider three cases here again. If the population variance or population standard deviation is known, so the 1 minus alpha times 100% confidence interval for the population mean is given by x bar plus or minus z alpha over 2, the population standard deviation divided by root n. So this provides this lower bound, which is x bar minus z alpha over 2 times sigma over root n, and the upper bound x bar plus z alpha over 2 sigma over root n. So this confidence interval is nothing but it is the construction of an interval on either sides of that of the sample mean. So from the sample mean we subtract certain value, and from the sample mean we added a certain value. So the construction of an interval on either sides of this sample mean provides the confidence interval for the population mean mu. And similarly, if the population standard deviation is not known, but if we know that the sample size is large enough, particularly if it is greater than or equal to 30, in that case, sigma could be replaced by the sample variance S. So everything else is the same. And in the case where the population standard deviation is not known and the sample size is actually small, particularly less than 30, in that case, instead of z alpha over 2, we have to use that of t alpha over 2 with n minus 1 degrees of freedom. So in this way, you can determine the range of values for which the null hypothesis is not going to be rejected, or we can construct that of the confidence interval for the population mean. So here we say that this confidence interval is nothing but the construction of an interval in either sides of the sample mean. So the one that is going to be subtracted from the mean, or the one that is going to be added from the mean, it is called margin of error. That is z alpha over 2 sigma over root n is subtracted from the mean, or it is added to the mean. So this is called margin of error, or this margin of error is nothing but half width of the confidence interval. Half width of the confidence interval from x bar up to the lower bound, we have z alpha over 2 sigma over root n, or from x bar to the upper bound, we have z alpha over 2 times sigma over root n. Therefore, this is the half width of the interval. So the full width of the interval is going to be 2 times this value, 2 times z alpha over 2 sigma over root n. But this d or z alpha over 2 sigma over root n is margin of error, or which is just half width of the confidence interval. So let's recall the example that we have considered on the mean life expectancy of HIV patients. So previously we obtained already the that's of the sample mean life expectancy and that's of the sample standard deviation. So let's construct the 95% confidence interval. And let's determine that's of the margin of error or half width of the confidence interval. So previously we have already calculated the sample mean as 54.41 and the sample standard deviation 4.859. We have the sample size 11, so the critical value is based on that of t distribution, which is actually 2.228. So what we are going to do is on this sample mean we need to add that of the margin of error to obtain the upper bound, and we have to subtract the margin of error to obtain the lower bound. So this is just x bar plus or minus t alpha over 2 with 10 degrees of freedom times the sample standard deviation divided by root 10. So this becomes 54.41 minus 2.228 times 4.859 divided by root of 11. And here in the upper bound, just this the minus symbol is replaced by the plus symbol. So finally the lower bound becomes 51.15 and the upper bound becomes 57.67. So this is the population mean life expectancy of HIV patients, or the population mean life expectancy of HIV patients is in between 51.15 and 57.67 years at 5% level of significance. And the margin of error or half width of the interval is nothing but here. It's just 3.2641. This is half width of the interval, which is called margin of error. Margin of error. Therefore, for all those values that are assumed under the null hypothesis, if they are in between this interval, H0 will not be rejected. But for those values outside of this interval, the null hypothesis would be rejected. And let's consider a second example on the cholesterol level of women. And let's construct the 95% confidence interval for that's of the mean cholesterol level of women of aged 18 up to 30. So the point estimate in that example is 178.2 and the standard deviation 45.3. So for that of the distribution, since the sample size is large enough 100, we have to consider that of the standard normal distribution, which is z alpha over 2, that is 1.96. So the 95% confidence interval for the population mean cholesterol level in women of aged 18 up to 30 is it becomes 169.32, 1 and 187.079. So half width of the interval is nothing but this one, 1.96 times 45.3 divided by root of 11. So this becomes 8.879 is half width of the confidence interval. So here you can say that the mean cholesterol level of women aged 18 up to 30 is between 169.321 and 187.079 at 5% level of significance. So this is all about today's video. Thank you for watching.